Welcome. In this video, we are covering XOR and XNOR gate. In the previous videos, we have covered the other logic gates. Check them out if you haven't seen them. And you can find the playlist in the description. Okay, let's continue with the XNOR gate. As you can see, the symbol is like this. Actually, the same situation here because the XNOR gate would need an additional transistor. We are going to first start with the less complicated one. So we have a bubble here representing the XNOR gate. Normally XOR is just like this. And you can see the Boolean representation of it right here. So we have a different symbol here. So the symbol here represents the XNOR gate, and you can invert it, the whole thing, and it turns into a XOR gate, which is represented by this symbol. And you can also convert it to the normal version. So this symbol would actually represent this part, but we also have a bar on top representing the inverted this bar on top here. Anyway, I'm not going to dive into too much detail, but people like curious about that part. Like this is that part basically. So doing the calculations from there, you can actually build an XNOR gate out of an AND gate, a NOR gate, and also connecting them together with an OR gate. So you can immediately see that 3 transistors for the AND gate, 2 transistors for the NOR gate, and 3 transistors for the OR gate. You might be able to like reconfigure this and make it less, but we are actually not doing it this way. We are going to use 5 transistors. Much lower than doing it this way. So you remember I said you can technically connect these transistors together and make like different configurations infinitely many different ways. By the way, I'm not sure if it's infinitely many ways, but this is a more efficient way, and I will show it in just a second. Okay, let's see the circuit. Here's the circuit. Let's power it up and let's read the output voltage, which is right here in this case. So we are reading 5 volt if both of the inputs are 0 volt. If either of them turns into a 1, we're going to read 0 volts. If both of them are 1, we're going to read 5 volts. If just both of them are different, we're going to read 0 volts. This is how an XNOR gate works. So in order to turn on the output, we're like reading a 1 on the output, both inputs must be the same. Okay, let's look at the logic right now. So we have a NAND gate here, and then we have a NOR gate here. And then we have a something here. It's not even like a gate. It's not like a NOT gate or something like that. And so what's going on here? As you can see, these are connected together. So the B are connected together and A's are connected together. So if you give 5 volts to A, let's say, and 0 volt to B, this one is not on. So we are not shorting ground to this location. We are reading 5 volt here. So 5 volt comes here. And 5 volt is went to the NPN, and the NPN is turning on. So we are sending 0 volts here. And because this one is off, but this one is on, we are shorting this 0 to the output. So if both of them are different, so one is 5, one is 0, this is going to be 0 volt. What about the other case? So let's say now both of them are 5 volt. This one is shorted to 0. This one is receiving 0 volt. This one is not turning on. So this is not connected to anything. It's floating basically. It's neither 5 volt or 0 volt. But because these ones are on, the 5 volt is read here. So we are not shorting the 0 volt here, and we read the 5 volt on the output. And so it's now not technically floating because this 5 volt here is going to come here, and there is no voltage floating here. So what about the 0 volt case? So on the 0 volt case, these are off, so we are not shorting 0 volt. We are reading 5 volt here. 5 volt turns on this one. We are receiving 5 volt here. Sorry, I didn't mean 5 volt like 0 volt. But because the other NPNs are off right now, this 0 volt is not shorted to the output. So we are reading 5 volt again. So this is a more efficient way to build the same thing with less transistors. It's like a genius way. And the same thing, the same XNOR gate, you can build it with PNPs, but that's gonna kind of invert the logic. As you can see, it's like the same thing, but kind of like inverted. So you need to connect a NOT gate in the end to reverse it back to normal. Which you would question then, what happens if you don't put this NOT gate here? Then you would get a XOR gate. So the symbol is like this, bubble is not there anymore, and the circuit is like this. Let's actually see that now. And so our output is right now here. Let's connect it there, which would be right here. And now my power is on. So these are both of the inputs. Sorry for the mess. If you get 5 volts to both inputs, you're reading 0 volts. If one of them is 0 volts, you're gonna read 4.7 volts. Yeah, this is why breadboards are kind of bad for this stuff, because the connections are not perfect and it creates a high resistance scenario where the voltage kind of was lower. And this is even now is kind of lower than what we were seeing before. Anyway, it's fine. So if inputs are different, we get a 1 on the output. If inputs are same, 0, 0 input, we read 0 volts. That is the XOR gate. Let's see what's going on in the circuit. 5 volt, 5 volt, 5 volt, 5 volt. So this is because this is a PNP. 5 volt was turning it off. So we are not shorting the 5 volt to this location. So we are reading 0 volts here. 0 volt was turning on a PNP. So this is turning on, 5 volt is being sent here. But because 5 volt is also not turning on these ones are off, and this 5 volt is not shorted to the output, and so we read it 0 volts. However, if you give 5 volt and one of them is 0 volt, again this 5 volt is not shorted to this red wire here. So we are again reading 0 volt here, we are shorting the same thing, we are getting 5 volt here, but one of them turns on, which would be this one, because we are giving 0 volt here, because of the blue one is 0. Then the output is shorted to 5 volts and we read 5 volts. If both of them are 0, this turns on, we are shorting 5 volts here, but 5 volt turns this one off, so we are not shorting 5 volts here. So this one is floating right now, 0 volt here, these ones are on. However, because nothing is connected here, we are shorting this location here, but there is nothing here. So we read 0 volts on the output because of the ground there. And this explains the XOR gate. And to make an XOR gate with NPNs instead of PNPs, you would basically just invert the output with a NOT gate. And I'm not going to cover that because it's the same thing. And here you can see the big picture. XOR gate with an NPN, you have to invert the output. XOR gate with a PNP, you don't have to invert the output. XOR gate with an NPN, you don't have to invert the output. XNOR gate with a PNP, you have to invert the output. And that's it. We have so far built all the logic gates necessary to build our 8-bit computer. You can find the previous episodes in the description. In the next video, we are going to cover half and full adder to then be able to build our ALU for the 8-bit computer. Thank you for watching.